Let's get started. So last time we talked about the conformal partial wave decomposition, and we wrote down a formula for the partial wave function for a 4-point function of identical scalars. So this is a 4-point function of identical scalars, and it's some CFT, and the omega subscript indicates that it's some physical correlation function. The partial wave is given by taking the physical correlation function and integrating it against a conformal 3-point structure. And this thing isn't supposed to represent a physical correlation function. It's just the unique function of x1, x2, and x that is consistent with conformal invariance given the representations of the operators appearing. So O, in most of what I'm talking about, has dimension delta and spin j, and I'm suppressing the spin indices. Phi tilde means it's an operator with dimension delta phi tilde, which, remember, is d minus delta phi. So given the dimensions and spins of all of these things, that gives you, in this case, a unique tensor structure, and we're integrating that tensor structure against the physical 4-point function to get the partial wave. And by the way, in the context of operators with spin, as Peter discussed, there are multiple tensor structures, and so the different choices of tensor structure would give you different partial waves, and all of those partial waves would appear in the conformal partial wave decomposition of correlation function. So this is the conformal partial wave, and because these integrals are conformally invariant integrals, it's fixed by conformal invariance to be proportional to the unique 3-point tensor structure associated with these representations. And so that means that it's just equal to some function of delta and j times that unique tensor structure. That's a consequence of conformal invariance. And then we took this expression for the partial wave, and we plugged it into the partial wave decomposition for the correlation function. So this is now an expression for the physical correlation function. And the result is that it can be expressed as an integral over conformal blocks, an integral over the principal series, times C of delta j. And C of delta j is just some kind of boring stuff times I of delta j. So this coefficient appearing here encodes all the dynamical information of the theory. It encodes the Opie coefficients and dimensions of the operators. Are there any questions about last time? Yes?
At one point you wrote down this correlation function with a bunch of v's, and then you inverted that, where v's were other operators.
Yes.
You said these v's, there's no restriction, they could be anywhere, but did you want to have them space-like separated?
So far, everything has been in Euclidean signature.
Okay,
so everything is space-like separated, yes. Everything so far is Euclidean signature. In a few minutes, we're going to switch to Lorenzian signature, and it will be very clear when that happens. Okay. Other questions? Good. So yes. So the Plancherel measure is known, and yeah, I forgot to copy it down into my notes again. Actually, I don't know if Peter's going to discuss this, but there's a kind of neat fact about the so the Plancherel measure for a compact group is just equal to the dimension of the representation over the volume of the group. So in this case, we have a non-compact group, and the Plancherel measure turns out to be so we have a non-compact group. But it has finite dimensional representations when delta is a negative integer. I think Peter mentioned that fact. He might talk about it more. So you can write down a formula for the dimension of those finite dimensional representations. And it turns out that the Plancherel measure is essentially just the analytic continuation of that formula from negative integer delta to general delta times a function that's periodic in delta, like some tangent or something like that. So it's actually not that complicated if you're familiar with the formula for dimensions of finite dimensional representations of the orthogonal group. But it's known, and I don't know if Peter's going to drive it. Probably not. Okay. But you can also look it up in that horrible book. Okay. Good. So, okay. So this expression for I of delta j expresses it in terms of this function. I should say I owe a lot to that horrible book, so I shouldn't call it that. What's that? This is being recorded. Yeah, that's true. We'll edit that part out. Okay. Good. So this expresses this. This is the thing we're interested in. We're getting it in terms of some function. So we want to write down something that just extracts this I of delta j without all of this stuff. And we have the technology to do that from last time. Basically, this is a conformal three-point function. So we should just pair it with the dual conformal three-point structure to get a number. So let's do that. So we find that I of delta j is equal to, so we just take a pairing of a three-point structure with this thing and a pairing of a three-point structure with this thing. And so when we pair the three-point structure with this thing, we just get the three-point pairing that we talked about before. And so I'm going to now divide by that. So we get phi O with phi tilde O tilde. This is the dual three-point structure that we're pairing with, inverse, times the three-point pairing with P delta J. And now I'm going to write out the formula for, well, no, okay, so I'll just write what that three-point pairing is, just the definition of the three-point pairing from last time. So it's an integral over all the points divided by the volume of the conformal group times the product of the things that we're pairing. Okay, so that's what the definition of the three-point pairing is. And now we'll plug in the definition of P. And so we get this prefactor times the prefactor from before times an integral dx1 through dx4 and also dx divided by the volume of the conformal group of the four-point function times two three-point structures. So let me take one of these integrals and put it right here, integral dx. And this thing I think we talked about before. This is just, that's right, we wrote the definition of this before. This is just a conformal partial wave, a four-point conformal partial wave. And before we had a partial wave with phi, O tilde, O, phi, and here everything is shadowed. So it's just the same thing where all the dimensions have been replaced by d minus the dimensions. So this is just another partial wave. And so we get what I'll call a Euclidean inversion formula. Because it expresses the function we're interested in that contains all the dynamical data, in terms of the integral of the physical 4-point function times a conformal partial wave, where the integral is over Euclidean space. And this may look a little bit formal because we have this 4D dimensional integral and we're dividing by infinity. So let's unpack this definition a little bit and get to something slightly more concrete. So yes, I did. Thank you. Any other comments or questions?
So this formula didn't require any principal series stuff that we did so far. And then it just requires the fact that the shadow operator with we just use the conformally invariant integrals that I think we saw in the homework, and then it's just is inverting that formula, right?
That's right.
I thought that the point of doing the principal series was to do something like show out that you deform the contour and set the poles or something.
The point of the principal series was to be able to write these formulas in the first place. So all of these formulas were only justified when delta was on the principal series. Once we've written them down, we can consider deforming the delta contour.
Delta external, delta internal.
Good. So the simplest setting is where delta external is also on the principal series. But it actually doesn't matter if all the delta externals are equal to each other. And the reason is that if the delta externals are equal to each other, then this partial wave is just some standard factors times stuff that doesn't depend on delta external. And the standard factors cancel between the partial wave and this thing. And so the analysis looks identical. The analysis looks the same if the external operators have equal real dimensions or equal principal series dimensions. So all of this is completely justified for external operators with equal dimensions. If you want to describe external operators with unequal dimensions that are not on the principal series, then you need to think about analytically continuing these formulas in the external operator dimensions.
So doing this, the self-integral does not become more divergent if deltas are all equal when you set this factors cancel.
Good. Okay. So right. So I don't have time to talk about. There are a lot of subtleties in these formulas, and I don't have time to talk about all of them in detail. But I'll say some words since people keep asking. So yeah, and they're good questions. So what does this formalism actually apply to? So what we did is we did harmonic analysis, which means that we could take a function on the group and we can express it in as a linear combination of matrix elements in certain irreducible representations. The irreducible representations appearing in the Plancherel formula are called tempered representations. So they're representations whose matrix elements are essentially square integrable. So they have some nice finiteness properties. And what you can do is you can decompose square integrable functions into these matrix elements. So this whole formalism is how to decompose square integrable functions on the group into matrix elements in representations. Physical correlation functions in CFTs are often not square normalizable. And an example where that happens is if there are operators appearing in the OPE with dimension less than d over 2. And you could see that there's sort of a problem if we write the 4-point function as an integral over the principal series, and then I said you're supposed to take the contour and deform it to the right and pick up all the poles. If there's an operator in the OPE with dimension less than d over 2, you're not going to pick up the pole for that operator. So you can ask what's going on. And the problem is that this formalism does not capture 4-point functions that include operators with dimension less than d over 2. So what you need to do is kind of annoying. You need to take the 4-point function. You need to subtract off all the non-normalizable contributions. And then hopefully you can get to some resulting thing that is square normalizable and that this formalism does apply to. You then do harmonic analysis for that thing and then add back the non-normalizable pieces. So it's a little bit of a pain, and I don't think that this procedure has been completely fleshed out in all possible scenarios. Yes?
Sorry, what does unitary
What is, okay, yeah, good. So unitarity of the underlying CFT should tell you that I of delta J has poles at positive real delta and with positive residues. And that's completely non-obvious from the stuff that we've been doing. So unitarity of the underlying CFT is some complicated and interesting constraint on all of this stuff that is not manifest.
This comment on the dimensions being equal and everything goes through, this extends to when they're equal in pairs and in some particular channel?
Yes.
As well?
Yes.
So this means that if the I delta J's, so you've got 1, 2, 1, 2, it's in the channel where you fuse 1 and 2, that it all goes through without any hitch?
It's in the 1, 1 to 2, 2 channel.
There's a channel.
Yeah. So generally, when you take into account all these subtleties, you do some subtractions, then you do harmonic analysis, then you add back the subtractions. That usually looks like some kind of modified contour prescription for this integral. Basically, after doing the whole thing, you find that actually, instead of doing the principal series contour, you're supposed to deform the contour in some funny way. And I think it would be nice and actually kind of important to work out all of that. My experience so far is that one shouldn't think of this as a non-starter for this whole set of technology. One should think of it as an insufficiency in the simplest form of the Planck-Charel theorem. The Planck-Charel theorem, mathematicians like to state it in its simplest form. In its simplest form, it takes tempered distributions to tempered distributions. It takes normalizable things to normalizable things, and that's a very simple thing to state. We're interested in applying it outside the usual regime of validity, but that doesn't mean there is no statement. It doesn't mean there's no theorem. It just means we have to figure out what it is. Yes?
How is the I delta J related to the OP coefficient?
How do you write down what?
How do you get the OP coefficients out of the I delta J?
Good. So the OP coefficients are the residues of the poles of I delta J. And I wrote that formula last time, and I want to keep going. So, but yes, so the OP coefficients are encoded in I delta J. So we'd like to compute I delta J. And this is a formula for I delta J. So let me unpack the formula. So remember, these quotienting by a non-compact group means we really have to gauge fix, insert a Faddeev-Popov determinant. And so let's do the same gauge fixing that we did last time for a 3-point function. So let's fix x1 to 0, x3 to a unit vector e, and x4 to infinity. And for the moment, we will leave x2 ungauge fixed. And when we do this, we get, so we have 1 over the volume of the stabilizer group. There's a Faddeev-Popov determinant factor that I won't actually write down because it's not important. So I delta J is proportional to 1 over the volume of the stabilizer integral over just x2 times the same thing where we've fixed 3 of the operator positions. And we've also fixed those positions in the partial wave. Okay, and so I could have gauge fixed all the way down to, so the next thing we're going to do is we're going to rotate x2 onto a 2-plane. So we're going to go to the usual configuration where all 4 operators are on a 2-plane parameterized by z and z bar. And I could have just jumped to that, and but you would have had to believe me for what the Faddeev-Popov determinant is. But if instead we start with this expression, which we've seen before, it's pretty easy to understand how to do the gauge fixing down to the 2-plane. The point is that this integral has some residual symmetry under rotation around this line, and we can use that symmetry to place x2 on the 2-plane. And when we do that, we're going to get a factor of the volume of the sphere swept out by this rotation. And so that factor, so this is then just, let's see here. Okay, so this is then just equal to 1 over volume of SO d minus 2. Here we're using the fact that the volume of SO d minus 1 divided by the volume of SO d minus 2 is equal to the volume of the d minus 2 sphere. times an integral over just the z-plane of the radius of the sphere to the d minus 2. So this is the volume of the d minus 2 sphere that we're integrating over in order to put x2 on a plane. And now we have something much more standard looking. We have the 4-point function as a function of z and z bar. This conformal partial wave can also be written in terms of a function of z and z bar. And I'll abuse notation and use the same letter psi to stand for that function of z and z bar. And when we do that, we have the standard dimensionful factors in this function. And when we specialize to this configuration, those turn into 1 over z minus z bar, z times z bar to the delta tilde, delta phi tilde.
Is there a volume SD minus 2?
Yeah, so this times that is the volume of the thing that we're additionally gauge fixing to put x2 on the 2 plane. And this thing can be written as z minus z bar to the d minus 2 times some powers of 2, factors of 2. Okay, so this is now a very concrete integral over a two-dimensional plane that you can try to do to determine this thing. Okay, so now we're going to switch to Lorenzian signature. The Lorenzian inversion formula.
Are there like cases where this integral has been done?
Yes, so you can do it in mean field theory. And when you do it in mean field theory, it's actually not a good idea to gauge fix in this way. It's a much better idea to work in this formalism where all the points are treated more symmetrically, and then you can do the integral. Other cases than that, I'm not really sure of. I think you can do the integral. You can formally do the integral starting from a Mellin representation, and it doesn't really give anything that looks immediately nice. Yeah, maybe for other simple 4-point functions, you can do it.
You really need to do both. Like this sort of looks like you're hitting the 4-point function with 2 3-point functions from the left and the right.
Sure.
So do you really need to do both? Like doing one of them sort of projects you onto.
Yeah, you're just describing the top formula there. So the point is just hitting it with one 3-point function is enough
To read off the OP.
to read off the OP coefficient. It's not going to be simpler than this, though. Doing that is essentially equivalent by conformal invariance to doing this, it won't give you a simpler integral. So, in fact, what you could do here is you could say, oh, let me just set x3 and x4 to my favorite values. So that's completely equivalent to this. It's equivalent to going through this procedure with the pairing and then going through this gauge fixing. Well, actually, it's equivalent to a different gauge fixing, but it's going to give you the same sorts of integrals. I mean, sometimes those are better starting points for analyzing what's going on. And in fact, the Lorentzian inversion formula can be proved sort of more easily by thinking in that way. Okay, so the Lorentzian inversion formula, due to Karen Huo, is a different expression for C of delta J. And C of delta J is just related to I of delta J by some boring factors. So the formula is for C of delta J. In the particular case we're interested in of identical scalars, it says that C of delta J is equal to some prefactor times an integral over a Lorentzian region that I'll describe in a moment. So the way that you know it's Lorentzian by looking at the formula is that it's an integral over independent real z and z bar. And that's only possible in Lorentzian signature. In Euclidean signature, z and z bar are complex conjugates of each other. And in Lorentzian signature, they are real and independent. So there's some measure factor. And then there's a conformal block. This is sort of the analog of the conformal partial wave, psi, in the Euclidean formula. Except this conformal block is pretty funny. It has dimension and spin swapped. And I won't really get to talk about it in detail, but this swap between dimension and spin is another example of an affine Weyl reflection. We saw that the shadow transform implements an affine Weyl reflection, which is a reflection on delta and j. In the case of the shadow transform, it only affects delta. That preserves the conformal Casimir. This is another example of a transformation on delta and j that preserves the conformal Casimir, but it's a bit more complicated. And it turns out there actually is a transform corresponding to this affine Weyl reflection. But unfortunately, we probably won't have time to talk about that. OK, and so this is times some factors x12 to the 2 delta phi, x34 to the 2 delta phi. And then instead of the 4-point function, we have a double commutator. So what this means is that, so the integral, I just wrote it as an integral over cross ratios. You should set these space-time positions to be in a configuration such that they give the cross ratio z and z bar. But this is a Lorentzian formula. The configuration you're supposed to consider. So let me draw. Here's a Penrose diagram for Minkowski space. The situation you're supposed to consider is where the points 1 and 4 are time-length separated from each other. And the points 2 and 3 are time-length separated from each other. And all other pairs of points are space-like. So I claim that there is a unique configuration of such points, at least let's restrict everything to a 2-plane. We can do that using conformal transformations. I claim there's a unique configuration on the 2-plane such that the points have these causal relationships to each other, and their cross ratios are equal to z and z bar. And that's the configuration you're supposed to use in this formula. OK, these subscripts? Oh, you mean these subscripts? OK, yeah, I'll write it bigger because it's important to keep track of. So that's 4, that's 1, that's 2, and that's 3. And it's important that the operators be in this kind of configuration where 1 and 4 are time-like from each other, because otherwise this commutator would vanish. Okay. So this formula is a different expression for the same thing, but it has some really, really nice properties, and we'll talk about some of them. But one of the things I want to do now, because I think it will be important for other lectures in this school, and it's nice material that somehow escapes most quantum field theory courses, is talk about Euclidean versus Lorentzian signature. And for example, our goal is going to be how to compute this double commutator. And I want to talk about that in detail because it's nice material. OK, so we're now going to talk about Euclidean versus Lorentzian signature. And that will be important for actually applying this formula. Okay, so so for simplicity, I'm just going to talk about a quantum mechanical system that's where everything is a function of time. I'm not going to worry about functions of space for the moment, and we'll specialize to quantum field theory later. So let's consider a quantum mechanical system with operators O. Then the operators in Euclidean time are just given by e to the tau h, O of 0, e to the minus tau h. And I'm going to use tau for Euclidean time, and I'm also going to put an e subscript on operators in Euclidean time just to try to disambiguate everything as much as possible. An operator at time 0 can be thought of as either in Euclidean time or Lorentzian time. They're equal to each other, so I'm not going to bother writing the subscript on operators at time 0. So here h is the Hamiltonian. If the Hamiltonian is unbounded in the positive direction, that is, if there are arbitrarily high energy states in the theory, then, and that's certainly true in quantum field theory, then the only sensible correlation functions in Euclidean signature are Euclidean time-ordered correlators. So a Euclidean time-ordered correlator is it's equal to the product of operators where we impose that the times are ordered correctly. And then plus permutations. So this theta function imposes that the times in the correlator are ordered from so that they're increasing from right to left. And the reason that only these types of correlators make sense is that if we expand this out, it contains a term that looks like O of 0, e to the minus tau 1 minus tau 2 times h. And then O of 0. So O1 of 0, O2 of 0, and so on. And this exponential factor is perfectly well behaved if tau 1 is bigger than tau 2. But if tau 2 is bigger than tau 1, then it's a horribly unbounded operator. High energy states get some exponential increase from acting with this operator. And the only way that you can, the only loophole that might allow you to consider this kind of thing is if this operator O2 for some reason has some extremely small amplitude to create high energy states. That might happen in some quantum mechanical system. It happens in finite dimensional quantum mechanical systems, but it definitely does not happen in quantum field theory. So in quantum field theory, or any quantum mechanical system like it, you simply cannot consider the case where tau 2 is bigger than tau 1. This just is not a sensible thing to compute. It's equal to infinity. So this really requires tau 1 is bigger than tau 2 to even make sense. So Lorentzian signature is different. So in Lorentzian signature, the operators in Lorentzian time are given by e to the I ht, O of 0, e to the minus I ht, where this O of 0 is the same O of 0 appearing there. So we can write that this is equal to O Euclidean of tau equals I times t. I'll use t for Lorentzian time. It looks like there are a whole bunch of plus or minus choices. And whenever I want to remember the correct conventions for this, I just write these formulas down. So the way that you know the correct signs in this formula are from this fact. You want, when you have a product of operators, you want the thing appearing in the middle to be exponentially damped. And that tells you that you need a minus sign here and a plus sign here. How do you decide what should happen in this formula? Well, in this formula, you want the thing that appears between two operators to be the standard Schrodinger evolution operator. And it was decided in the early 20th century that that should look like e to the minus IH times T1 minus T2. And that decision has forced on us a convention for what I means for the rest of time. And so that tells you that you need a minus I here. And that fixes the relationship between tau and IT. So there's only one correct answer for all of these things. And you can just write down these 2 lines to remind yourself what it is if you forget. OK, so now in Lorentzian signature, you can now consider a much bigger zoo of correlation functions. Because we can now, for example, consider a Whiteman function. So this a Whiteman function just means a correlation function. We can consider it at arbitrary real Lorentzian times. So this makes sense for any T1 through Tn that are real. OK, so the reason that the Euclidean time-ordered correlation functions made sense is that if the operators were in time order, then we get exponential damping of high-energy states. And so if we insert a complete set of states, the sums converge nicely. In this case, in Lorentzian signature, we have factors like e to the I T1 minus T2. And instead of being exponentially damped, the contribution of high-energy states is highly oscillatory. And the fact that it's oscillatory doesn't depend on the sign of T1 minus T2. So we can have T1 minus T2 be positive or negative, and we get that high-energy states are highly oscillating. This is good enough for the sum over high-energy states to make sense, at least in a certain sense. So you might worry, well, you know, just because you have an oscillatory sum doesn't mean that it's well-behaved. And in fact, that's kind of true. There's a slight technical subtlety here, which is that Whiteman functions are really only well-behaved after you integrate them against a smooth test function. So what we should really do is integrate the Whiteman function against the test function, against a bunch of test functions. For example, you could study the Fourier transform, which would be the integral against a certain type of test function. And doing this is actually a good thing because these smooth test functions turn that highly oscillatory behavior into damped behavior. So once you integrate against these smooth test functions, you really do get something that's truly nice. So the statement is that Whiteman functions should really be thought of as distributions and not functions. They really only make sense after you integrate them against something. And one of the axioms of quantum field theory is that they should be so-called tempered distributions, which means in particular that these things that you integrate them against should be so-called Schwartz functions. If you want to find out what that is, you can wait for the lectures by our colleague Wikipedia. So actually, I didn't really understand this stuff when I was for a long time. looking at something like this always made me really uneasy because it's a really stupid thing to do in Euclidean signature. In Euclidean signature, well, you might want to do it anyway. Sometimes you actually do want to smear things. But in Euclidean signature, the annoying thing about doing this is that only time-ordered correlators make sense. So if you start smearing the operators around, you're kind of mixing up different orderings of the operators. And it makes it extremely hard to insert complete sets of states and understand what's going on. So it really messes things up. But in Lorentzian signature, you're never changing the ordering of the operators. So this smearing is totally fine, and in fact is kind of a nice thing to do. So there's a big difference between those two cases.
I mean, when the keys come together, you still have singularities. You have to somehow decide how to figure it out.
So good. So we'll talk about I epsilon prescriptions in a second. These distributions, these Whiteman functions, should be thought of as boundary values of holomorphic functions, and that actually tells you that uniquely fixes the prescription that you should use when you reach singularities. So it's true that Whiteman functions can have singularities in time, but they're uniquely defined as a distribution. There's only one correct way to treat those singularities. So this is a completely unambiguous thing to do. By contrast, when you're smearing things in Euclidean signature or you're smearing time-ordered correlators, there absolutely can be ambiguities in your definition of what they mean, and that's what we call contact terms.
But in practice, since you have this I epsilon or this prescription to integrate, this statement does not limit the strength of the singularity when two times collide, right?
It does not. It can be a very strong singularity, but the singularity but when you smear, the thing that you're encountering is something like the integral dt of 1 over t plus I epsilon to the 10 to the 20, 10 to the 90. So this is an extremely strong singularity, but the answer is equal to 0. It's not 0. What is it? Pi I. What? No. It's a pure power. What am I? Oh, yeah. It's 0. It's 0. So, yeah, that's all singularities of Whiteman functions are like that. And once you realize that, then you can grow to love smearing, or at least live with it. Okay. Good. So as I mentioned, what time did I start? Anyone know? 30? Okay, thank you. So as I mentioned, Whiteman functions are boundary values of holomorphic functions. And what that means is that if we start with a Whiteman function, then we can safely give these t's imaginary parts. And when we do that, these oscillatory factors become slightly damped factors. Absolutely. So this only works. We can only do this if the epsilons are ordered. So if you take this Whiteman function and you move in the correct way into the complex plane, that is, you move in such a way that the imaginary parts of the times are ordered in this way, then everything is nice. You never encounter a singularity. All high-energy states are exponentially damped. And this Whiteman function actually becomes a holomorphic function of t in this region. So holomorphic in the t's in this region. So staying in this region, you can now imagine taking tk to 0. So I'm not sure if I can draw this. So we have this is the boundary of the region. This is Lorenzian. This is the Lorenzian correlator. We move out by a little bit into the holomorphic region. Out here, this is bad. There are dragons. So don't go that way. We go this way, and now everything's holomorphic, and we can move down here. And once we get down here, we actually get to a Euclidean configuration. Okay, so by analytically continuing, we get to OL1 of minus I epsilon 1, OLN of minus I epsilon n, which is just by that formula equal to a time-ordered Euclidean correlator. And so now we can run the logic backwards. So suppose we want to compute a Whiteman function. The correct prescription is to start with this Euclidean correlator. And the way you get this Euclidean correlator is just by taking the time-ordered Euclidean correlator and putting the Euclidean times in the order that you want the operators in. So here we're interested in studying a Whiteman function O1 through On. So we put the Euclidean times in increasing order from right to left. And when we do that, that means that the time-ordered Euclidean correlator will be equal to this correlator. And this can now be analytically continued backwards to this correlator. And we finally take the epsilons to 0 at the end. Okay, so I'll summarize that. So to compute a Whiteman function, or Whiteman distribution, first start with the Euclidean correlator. Set the Euclidean times to the same order as the operators you want. Analytically continue. I guess we could say analytically continue the Euclidean times in the complex direction. Ooh, let's see, what do I want to do? Yeah, so we take these Euclidean times and we send them to the same Euclidean time plus I times tk. This is perfectly okay because the operators are separated in Euclidean time, so the correlator is completely holomorphic in this region, so we have no problem doing this. And then finally, set the epsilons, take the limit to 0. And when we take the epsilons to 0, we might have an object like that. The limit as epsilon goes to 0 of that thing looks pretty scary, but it's perfectly well defined as a distribution. It's not a nice function, but it's a nice distribution.
This does not follow from your reasoning. It's just some theorem that you say is true. It could be that that integral just blows up.
You mean that the distribution you get could be bad?
Yeah, well, no. I mean, so you integrate over f's, and now let's take the limit when epsilon goes to 0.
Yeah.
Distribution means that you get a finite answer.
Yes.
So I'm just trying to see. It does not follow from anything you
I
said.
have not proved that statement. That's right. Yeah. That's absolutely right. That's a theorem. yeah, I'm going to have to appeal to that theorem.
But why? I thought you were saying that if you integrate to the right of this dragon length, then you don't need to be, even when epsilon goes to 0, everything is analytic to the right, so you can deform the integration contour. So doesn't that show that that will be fine?
That's right. So if you're integrating a test function that is itself a holomorphic function in that region, then you're fine. Because then you can do exactly what you said. You can take the integration contour and you just pull it away from the dragons. So it's out here, and then it's manifestly finite, and everything's OK. So you need the theorem if you want to talk about test functions that are not themselves holomorphic functions in this region. And I think the statement is that if they're Schwartz functions, then the answer is supposed to be well-defined.
This, of course, will not be true for a generic function of n variable. It's a function that comes from a quantity.
Yeah, I have to apologize. I don't know what all the assumptions are that go into this. I mean, I think I think this is part of Osterwalder-Schrader reconstruction. So they show that if you start with a reflection positive CFT and reflection positive QFT in Euclidean signature, then you can Wick rotate it and get a good QFT in Lorenzian signature. Part of the definition of a good QFT in Lorenzian signature is that Whiteman functions are tempered distributions. So I assume they prove this in the reconstruction theorem, but I don't know.
But now we are just in quantum mechanics, so presumably it should be trivial.
Yeah, maybe it is. OK, good. So let's do this procedure to compute the double commutator in Lorentzian inversion formula. So what we're going to do is we're going to start in the Euclidean region in the following configuration. We want to get into a region where 1 is in the past of 4 and 2 is in the future of 3. So here I'm drawing the light cones of 4 and 3. We're going to take 1 and move it that way into this Lorenzian region, and take 2 and move it that way into this Lorenzian region. We can use, I'll use light cone coordinates. So this direction is u, which is x minus t, and this direction is v, which is x plus t. When we start in Euclidean signature, everything is space-like separated. There are no branch cuts. Everything is beautiful. And the interesting thing that happens is when we start moving 2 and it crosses the light cone of 3. When that happens, we're going to encounter a singularity, and the I epsilon prescription will tell us how to move around that singularity. Similarly, when we're taking 1 and we're moving it into the past of 4, we're going to encounter a singularity when 1 becomes light from 4, and the I epsilon prescription will tell us what to do with that. So we're interested in computing a double commutator, but let's just consider one of the orderings. And we're going to compute what happens for this one ordering, and then I'll just write the answer for the other orderings. And we'll take a linear combination to get the commutator. OK, so we want the operators to be in this order. And the way we achieve that, so in particular, we want 2 to be after 3. So let's keep x4 and x3 just in Lorenzian signature with no I epsilons. And to get 2 to be after 3, we'll take T2 and give it a small negative imaginary part. And we also want to make sure that 1 is in the past of 4. So to do that, we're going to take T1 and give it a small positive imaginary part.
Your notation is x is the original correlator is the Euclidean one?
We're going to start in this Euclidean configuration where all the times are 0. And we're going to start moving them along these paths.
So the times are 0?
They start at time 0. That's right. So we're going to start at time 0, where all the times are 0. We're going to give the times some small imaginary parts. And then we're going to start changing the times. Specifically, we're going to start changing the v coordinates of everything. OK. So actually, when we make this choice, what we've also done is we've forced 5x2 to be to the left of 5x1. So if you look carefully at what we're doing, and in fact, we're really putting 5x2 to the left of everything. So that's not what I wrote here, but it's okay, because we're going to stay in a region where 2 is space-like from 1 and 4. So, okay, so the actual correlator we're computing is 5x2, 5x4, 5x3, 5x1. But this thing will be equal to this thing in the kinematics we're interested in, because operators at space-like separation commute. If I wanted, I could have just given all the operators some I epsilons and ordered the I epsilons in the right way, and that would have been just a little bit more annoying. So we're just going to do this. Okay, and so now what we're going to do is move the operators, and we're just going to move them in the v direction. So we're going to keep u fixed. So this is equivalent to taking v2 to v2 minus I epsilon and v1 to v1 plus I epsilon. Maybe I'll keep that up there. Okay, so the interesting thing will happen, again, when we cross these light cones. And so when we do this, the z cross ratio is completely fixed. The z cross ratio depends only on the u coordinates, the u light cone coordinates. So it's completely unchanged. The only thing that is moving when we do this is the z bar cross ratio. And that we can write as v21, v34 over v31, v24. And 1 minus z bar is v32, v14 over v31, v24. The reason I'm writing 1 minus z bar is that nothing particularly interesting happens to any of these factors here, because none of these factors is going to 0 when the interesting light cones are being crossed. But the light cones are going to be visible in these factors in 1 minus z bar. And I also wrote these in such a way that in our initial configuration, all the factors are positive. So the name of the game is going to be to keep track of the phases of everything. Everything's going to start out positive. And now we're going to continue into this regime, and we're going to keep track of the phases. So specifically, let's look at v32. So when we do this continuation, we start at positive v32. And because we're giving v2 a small negative imaginary part, v32 is positive, but it's like slightly above the real axis. And now we start moving up that way, which means v32 is decreasing. And we're moving it in such a way that we never change the Euclidean times of anything. We never change the imaginary part of these, so we just go in a straight line like this. And we end up over here. And what this means is that the phase of v32 changes by e to the I pi. Not e to the minus I pi. That's what would have happened if we went that way. We're going this way, so it changes by e to the I pi. And the reason I'm being pedantic about that, you'd say I pi is the same as minus I pi, but the point is that correlation functions can have fractional powers of v32, so we really need to keep track of which direction it goes around. Okay, so similarly, v14 starts out being positive with a small positive imaginary part, because v1 has a small positive imaginary part, so it goes to e to the I pi v14. And this means that altogether, 1 minus z bar goes to e to the 2 pi I times 1 minus z bar. So we start in the Euclidean region. So now let me draw the z bar plane. We start in the Euclidean region where z bar is between 0 and 1. as we move into the Lorentzian region, z bar moves towards 1. It goes around that way, exactly that way, and then comes back to the real line. And I don't know if, well, OK. So that's what happens in this particular ordering. And this particular ordering is actually an interesting ordering for one reason it's an interesting ordering is that it's equal to the time-ordered correlator in this kinematics. So to see that, it doesn't have to come back to itself. It just, yeah, that would be the, if we wanted to write, yeah. It just goes back to somewhere on the real line, where the position on the real line depends on where x2 ends up. So this ordering is equal to the time ordering in this configuration, the Lorentzian time ordering. To see that, you can pick a time coordinate that runs that way, almost at a 45-degree angle. And you can see that the ordering goes like 3, 2, 1, 4 in that time. So if you're interested in time-ordered correlators, this is the prescription for how to get to this interesting kinematics. You fix z. You don't do anything interesting with z, but you take z bar and you move it around 1 in a counterclockwise direction. OK. Yes?
There could be some interesting physical configurations which respond to complex z and z bar. Is it just a coincidence that now we are focusing on real z and z bar?
So if all the points are in Lorentzian signature, then I think you always have real z and z bar. The reason is that, well, let's see. Yeah, well, this is true in a 4-point function. I'm not sure what the statement would be for the cross ratios in a higher point function. But in a 4-point function, it's definitely true, because you can use conformal invariance to put everything on a 2-plane. And in a 2-plane, the cross ratios are just ratios of differences of v's and u's. And v's and u's are real in Lorentzian signature. If you think about something like the row coordinate, then the statement is that the row coordinate is always either on the real line or on the unit circle. OK, so let's summarize what we just found. So this particular ordering, phi 4, phi 1, phi 2, phi 3, is equal to what I'll write like this. So g of z and z bar would be the usual 4-point function with the dimensional factors stripped off. And what this notation means is you're supposed to take z bar around 1 in the indicated direction. And we can do something. We can do the same exercise for the different orderings. And this is definitely an exercise that I recommend. So if we look at the ordering 4, 1, 3, 2, so this is what we would need to subtract from this to get the commutator of 2 with 3. Then that turns out to just be equal to g of z and z bar with no continuation of z bar. So it just stays between 0 and 1. If we look at 1, 4, 2, 3, this turns out to also be equal to the same thing with no continuation. And if we look at 1, 4, 3, 2, this is equal to g where we continue the other direction. And this is, I absolutely recommend you do this exercise to make sure you are comfortable with what's going on. And you might be wondering, why on earth did these particular orderings give no continuation? What's significant about those orderings? The thing that's significant is that, so this ordering, for example, can be written in such a way that operators 1 and 2 act on the vacuum. The reason is that 1 and 3 commute. 1 and 3 are space-like separated in this kinematics, whether 1 is over here and 2 is over here or not. Just in the entire process, 1 and 3 remain space-like separated. So this ordering is equivalent to 4, 3, 1, 2. And it's an old theorem due to Mach that the OPE converges if the OPE between two operators converges if the two operators act on the vacuum. So Mach says that the OPE, the 1, 2 OPE converges in this ordering. So it means that if you remain in this ordering, no matter where you move the points around, as long as you remain in this ordering, it must be that Z and Z bar remain on the first sheet. They remain in the regime of cross ratios where the OPE converges. And that's the regime that Dolly Mill talked about. It's the entire Z and Z bar plane minus the cut from 1 to infinity. So in particular, if you're in this ordering, you can never get Z or Z bar to go through the cut from 1 to infinity. And that's the reason that you end up with these things with no continuation. So the final result is that the double commutator that we're interested in is equal to this combination of continuations. And this is sometimes called the double discontinuity, or more precisely, 2 times the double discontinuity of G. So in the last 5 minutes, I want to use this to do the light cone bootstrap using the Lorentzian inversion formula and recover the formulas that we had in the first lecture. And I promise that it'll only take 5 minutes plus a few minutes. Okay, so what we're going to do is, we're going to do large spin perturbation theory. And the way you do that using the Lorentzian inversion formula is pretty remarkable. You just set J to be large. So when you do that, the funny conformal block you can think of this, so J is sitting in the slot usually reserved for dimension. So this has some factors that look like this. So large J pushes you away from Z and Z bar equals 0. It pushes you away from the S channel towards the T channel. So in particular, it will be important for us that this pushes us towards Z bar equals 1. And the reason I'm not talking about Z is that, so first of all, in the Lorentzian inversion formula, you're integrating over a square. There's a symmetry of this square. So we can focus on just the upper triangle. And it turns out that poles, you can try to convince yourself that poles can only come from the region of small z. We're interested in poles because those encode the OPE data of the theory. So poles come from this, this region of small z. And then large J is pushing us up here. So everything is going to be, so here's large J. So all the interesting stuff is going to be happening near this point, which is the double light cone limit, which is the same point that we saw was controlling the light cone bootstrap earlier. Okay, so because poles are coming from this region of small z, we can use our light cone approximation for this conformal block. And let me include the measure factor from the inversion formula. So the light cone approximation for the block that was on your problem set and that we used heavily in the first lecture says that this is equal to, at leading order, 1 over z to the d z bar squared times z to the j plus d minus 1 minus delta minus d plus 1 over 2 times an SL2 block, k delta plus j of z bar. And we can just cancel some factors, 1 over z, z to the minus delta minus j over 2, 1 over z bar, k delta plus j of z bar. Again, I'm going to keep that formula up there. So that's the funny block times the measure. And then we're going to use large J in that we're being pushed towards the T channel. We're being pushed towards small 1 minus z bar, just like we were in the last lecture. What that means is that we can study the light cone expansion for the 4-point function in the T channel. So this formula appeared in the previous in the first lecture. This is an approximation for the 4-point function using the T channel OPE in the light cone limit, where light cone limit in this case means small 1 minus z bar. So the leading contribution was from the unit operator, and then other operators in the T channel. Prime stands for prime means it's in the T channel. Other operators not equal to the unit operator in the T channel contributed with their light cone blocks which are approximately equal to some power of 1 minus z bar times an SL2 block of 1 minus z. Okay, so now the last thing we need to do is compute double disk. And double disk is some procedure that you do on z bar, so it really only cares about the power of z bar. And so if we take double disk of this factor, 1 minus z bar, to the tau prime over 2 minus delta phi, we have to do this analytic continuation. But the analytic continuation around 1 just gives us a bunch of different phases. So we get some combination of phases. We have to add them up. And the result is equal to 2 sine squared pi tau prime over 2 minus delta phi. So 2 comments. First of all, this is positive. Second of all, it's bounded. Pardon? Yes, thank you. Times the same thing. So this inserts a factor here that's positive. It's bounded. It's less than 2, less than or equal to 2. And both of these facts will play an extremely important role in Tom's lectures. It should remind you of Joao's lecture where I think he wrote something like that. In ADS, these are the same, I believe. I don't know if anyone's going to talk about that, but and then the last comment I want to make about it is that in the light cone bootstrap before, we had a funny factor in the anomalous dimension that was something like this. And it was responsible for the suppression of double trace contributions to the anomalous dimensions of, the suppression of double twist contributions to the anomalous dimensions of double twist operators. And I said there was some deep physics behind this factor, and this factor is really this factor. So it has the same double zeros at double twist locations, and it's coming from the double discontinuity. And this fact is quite powerful, and I think it's one of the main reasons that the Lorenzian inversion formula is so interesting and has been so useful in the analytic bootstrap. Because of this factor, double twist contributions are highly suppressed, and if you're working in a theory with a small parameter, sometimes you can argue that double twist contributions are just 0 at some order in that small parameter. What this really means is that d disk of G can be much simpler than G. Just to give a concrete example, in the Wilson-Fisher theory in 4 minus epsilon dimensions, if you take d disk of the 4-point function, then the only operators that contribute to leading order are the unit operator, the only operators that contribute up to order epsilon cubed are the phi squared operator. So this is G for a 4-point function of phis. So this equality is true up to order epsilon to the 4th. So you can completely fix all the OPE data of the theory up to 3-loop order by taking d disk of 2 contributions and putting them in the inversion formula. Okay, I'm going to take my remaining minus 3 minutes to just do the integral for you and recover one of the formulas we had from last time. So let's put everything together, and let's focus on the contribution of the unit operator to this C delta J. So this is equal to some factors, some gamma functions coming from up there that I won't rewrite, times the double discontinuity, which contributes this factor of 2 sine squared pi delta phi. And then we get an integral over a square, and in this approximation, these limits that we're taking, the integral over the square factorizes into a part that depends on z and a part that depends on z bar. This integral over z produces a pole at delta minus j over 2 is equal to delta phi. This is exactly the double twist. This exactly corresponds to double twist operators, the ones we talked about last time. It shows you that at very large j, the correlator is dominated by double twist operators. And this integral turns out can actually be done exactly. And when you so when you take these gamma functions, so here, by the way, h bar is delta plus j over 2.